Yeah, hi, my name is Mike Rucker and I'm going to talk about the Ubuntu bootloader now. First of all, quickly about me, I work on the Linux kernel, Ubuntu bootloader, open and data stuff. I'm a maintainer in these projects one way or the other. I do PJ work as a hobby as well. So that's about me. I decided to split the talk into a couple of sections. So first of all, I would like to introduce you to what the bootloader is at all, what the Ubuntu bootloader is, what it can do. Then I'll have a brief newsflash for those people who already did some Ubuntu work so that they know what happened in the latest releases, so I can sync them up. And this will be really brief. After that, I'll go into the Ubuntu porting. I'll tell you how to get the sources, how to compile them, how to configure the stuff, how to add new stuff into the Ubuntu. I'll talk about the driver model, which is a recent development. I'll talk about the device tree control. And once we build up all that knowledge, doing a Ubuntu port for the architecture for it is going to be really trivial because you will have the understanding of the stack. So we'll do that in the second half of the talk. And since enabling all that stuff will make Ubuntu grow in size considerably, we'll talk about low memory systems. And then we'll wrap it up and move on to the next one. So, what is a bootloader in the first place? Well, you see, when you power up your computer or system or whatever, there has to be some code which does some basic initialization of the system and make it possible to load the next stage and execute the next stage. And that's the bootloader's task. Now, in modern systems, it just so happens that there are multiple bootloaders which are kind of chain loading one another. You know, think of any modern SoC has a boot drum on it, and when you flick on the power, it just jumps into the boot drum is executed, does some initialization, then loads some stuff from whatever SD card, and executes that stuff in OCRAM. The stuff in the OCRAM usually initializes DRAM, loads more stuff from maybe SD card, maybe some other storage into the DRAM, and that's typically the first bootloader which you can replace. And that's responsible for starting the Linux kernel. So this kind of chain loading happens nowadays. It's the same on Intel where you have like this behind us which kind of starts your graph and that starts the kernel, that kind of thing. So that's what bootloader does. Ubuntu is one of these bootloaders. There are alternatives, but Ubuntu is like the omnipresent bootloader on most of the Architect boards. I said, yeah, it's capable of loading Linux, stuff in Linux. That's true, but it can also do much more. It can behave as a boot monitor, debug tool. So, basically, you can drop into the Ubuntu shell, build registers, and do more other stuff. To give you an idea how the board looks when you start Ubuntu, this is what you get. This is usually the first print out on the board, what you get. What you see here is the Ubuntu version. CPU type, board model. In case you're reporting some bugs in Ubuntu, please include at least these information and with which Ubuntu sources did you use to compile that stuff, because sometimes it's just some vendor hacked up crap and we cannot help you with that. If you get mainline Ubuntu, well, we'll kind of figure it out and we probably can help you with it. So what else we have in that print is some information about the hardware which is available, how much DRAM you have. On this board you have some TMMC controllers, serial port controllers here, Ethernet, whatever. Ultimately you reach the out-the-boot countdown. Now if you let it come down to 0, you would go execute this out-the-boot command, which usually means start Linux. It can be anything, but in the most cases it's just like load Linux from somewhere, start it, and that's where you end. Now you can interrupt that out-the-boot countdown, and then you will drop into the Ubuntu shell where you can do a lot of stuff, like for example execute the help command, which is really helpful. That also tells you what that Ubuntu port supports. Usually you can, in this case I'm reading memory, you can do a lot of other stuff, write memory, you can poke the registers, you can access different buses, that's like I2C, SPI. You can access storage, UNC, again, SPI flashes, empty devices, UNC storage. You can access Ethernet, you can do download files, and so that's what you can do with Ubuntu. And if you explore the help or the uniques, you will see what else you can do. Now, this is a brief news slide about what's new in Ubuntu in 2018 and what happened in the last year pretty much. So we're continuing conversion to device tree control and driver model. At this point, we only have like legacy drivers which are not yet converted, and most of that is probably going to be removed and going away because no one really cares about that anymore. So we'll just nip it out from the code base. In case you still have some legacy devices and want it out, patch is welcome. We also got FE support in U-boot, and what that's for is you can navigate like an FE library and execute FE applications. So this is, for example, useful if you want to change the graph from U-boot and make it look like kind of like the graph you're used on PC. At that point, you can execute the graph FE application, and the graph FE application is calling into the U-boot, which is providing services like serial code access, storage access. So that sort of thing. In case you're building some sort of dev board, you should probably enable that. Related to that is distro boot command support. Again, if you're building a dev board, you should enable that. It allows you to set up some sort of standardized U-boot environment which the distribution can count on, and then it's easy for the distribution to generate boot images and boot them on your dev board. So they can look into that. Oh yeah, we are also doing CI recently, which is cool. So if you used to submit patches to U-boot, and you were asked to build it for like these 10 architectures, it kind of sucked because you had to get all these cross compilers and it was kind of mess. Nowadays you can just push it to GitHub and there's a Travis CI, Travis YAML file, something like that. YAML file which will trigger the Travis automatically, will do the CI run to enable that. And you can just collect the results on the patch node and they'll release for all the architectures. One last thing we did recently is device tree application, device tree overlay application. Now, what that is about is since this sort of situation with configure as device tree overlay loader in Linux, not finding its way in mainline like ever, probably. It was pushed down into the bootloader so that U-boot is not capable of applying device tree overlay to the device tree and then passing this patch device tree to Linux. And recently we also support for that image, so you can have a fit image with Linux kernel, device tree, fragments, and in the fit image configuration, you can specify which kernel you want to use, which device tree and which fragments should be applied to that. And you will assemble that and just put it in Linux kernel. Now, if you have no idea what that means, it doesn't matter really. This is just really advanced stuff. By the way, about this device tree overlay, there might be a change in the overlay format, so be careful about using that stuff. Okay, now let's get to forcing U-boot. So first of all, obviously you need to get the sources if you want to do any U-boot porting or any U-boot work. You can get them at the Steam repo, it's accessible through Git and HTTP, so if you have like some sort of crappy corporate firewall which doesn't let you get protocol, you can use HTTP. Usually you should use the Git master repo because everything is there. But if you're working with one of the maintainers and he says, yeah, well, in my subtree there is some feature and you need that feature, so get it in the subtree, it's a little like here. And once you have the sources, you would probably want to build them, right? So it's really good. I would just clone them, change the directory into the source tree. If you're cross-compiling, you need to export this to variables, cross-compile the prefix and the architecture name for which you're cross-compiling. It is not necessary to do that if you're compiling natively or if you are building a sandbox target. If you're not doing that, you will also need the cross-compiler, cross-utils, and that sort of stuff. Now, when you have all that set up, you can do make board underscore get config. Obviously, you need to have that board supported. This will configure the U sources, and then you can update it or produce the U binary and then put on the board. The board has to be supported. You can check if the board is supported by looking into the config directory in the U source tree. If your board is not supported, well, patches are welcome. I think we support like 500 boards, maybe more. I would have to check that. So I mentioned the sandbox target. This is kind of interesting because you can compile the U-boot as a Linux application and you can launch it in your Linux system and then play around with the U-boot shell, and you can also use it for some tests in case you're doing some work on the U-boot shell. For that, you don't need to proxy compile, you just run make assemble that config make, and it will just release U-boot, which is under Elf binary, so you can just like /U-boot, and you will get the shell, and you can play around. That's what I mean. Alright, but if you want to do some work on the U-boot besides compiling it, you probably should know where everything fits. So the hierarchy of the U-boot source tree from this, you have the arch directory, as well all the architecture specific stuff, the common stuff goes. So you'll have like arc, NMN, for example, arc mix, whatever. That's where the common stuff for that architecture goes. You will also have there's some directories mark-foo, where foo is like code specific to the SOC in that architecture. You can think of that like Max of FPGA for Altera of FPGA, which is an encore in there, and SOC, or Mach PCM for the chips which are in the Raspberry Pi. You will also have device resources there in the same place, and this are sources for the U-boot control device tree. This is not passed to the Linux, so the device trees which are passed to the Linux are separate from that. What else do we have here? Board files are in board. Usually when you do a new U-boot port, there shouldn't be that much stuff which you need to add into the board. All that should be in drivers or in the device tree. We have the configs I mentioned earlier. This is the configs configs for the U-boot. We also are still in the process of converting the legacy config macros to the config, so we will find some legacy configs and then config / your board domain. Unfortunately, yeah, this is work in progress. We're replacing that. Then we have the drivers, even commands and implementations, network stack, file systems, and some of the here. Now, if you look into the U-boot sources, you will see that there are config files and make files all across the U-boot hierarchy. That implies we use kconfig for configuration of U-boot, just like the kernel, we use kgo for building U-boot nowadays. So you can do the usual stuff like menu config, just like you are using the kernel. You'll get a nice same versus menu that will be available there. I mentioned we're still converting to that, so there are some symbols which are not converted. So in case you're looking for them in this make menu config, you don't find them. It could be that they are still not converted, and then you can change this whitelist file if they are in there. And then they will have to go into include /config /your board page, or you can convert them to kconfig, send us a patch, which will be amazing. Thank you. Now, all new options, in case you decide to add any new kconfig option, it has to be kconfig only. There's no way in hell you are adding non-kconfig option. It just won't fly, not happening. And to give you an idea how the kconfig stuff looks like, I picked this driver's net kconfig file, right? So what you see here is the symbol config vmph. So if you like to make menu config, you'll be able to find that there is the vmph symbol somewhere in the included menu. So what do we have here? The symbol is Boolean. So if you didn't make menu config, you will find some entry which will say this. You can turn it on and off with Boolean. It depends on another symbol, which is the element, and there's some help associated with that. Now there's a little quirk in that if you enable the vmph, it will actually show up as config underscore vmph in your .config file, and that's been picked by the cable system to operate these symbols. So in the make file, so when the make file actually gets evaluated, this will attempt to object that y in case config that Altera PSE is enabled in the kconfig. Right, that's pretty much it. Now, if you want to add any new stuff into the kconfig table files, just edit the matching kconfig, add similar entry as you saw on the previous slide. You have some sources associated with that, add the make file, add the sources, and that's it. It's that simple. Now, one thing which I would like to ask you is not to add hardware-specific stuff on platforms which are DT capable. So if you have a platform which is DT capable, you should add hardware-specific or hardware topology-specific stuff into the device tree instead of hard coding it into the U-boot or into the kconfig. system. So speaking of device tree, what is a device tree? Well, how many of you actually do know what a device tree is? Very good. Super. That's nice. So yeah, the device tree is a structure which is used to describe hardware topology software. It's not the case always that you can probe the hardware topology. You can think of like an SPI controller which has some devices hooked on it, and you just can't figure out what's on the other side of the box. That's why I device tree. And we use that to describe the entire topology of the system. You can pass it to you, you can pass it to Linux, doesn't matter. It's actually standardized, the device tree. You can find the standard in this e-paper documentation and further details on the device your website. Now, it can have multiple representations. One of them is the device tree block, the other is texture representation. There is also a YAML representation of the device tree, but I don't know what state that is. And instead of going into like the specific details on how the device tree looks like, I'll just give you an example. So this is the device tree pulled from U-boot actually, but it's the same in U-boot. So U-boot and Linux are sharing the same device tree file. There are a couple of specific words to U-boot which we try to kind of keep separate, but the device tree files should be mostly the same. So what you see here in the device tree at the beginning, there's an include directive. This is just because both Linux and U-boot are running the device tree through C preprocessor to expand these macros here, so that you don't have to encode numbers into the device tree by hand. So you can just use these symbols. And besides that, what do we have here? We have a grid node marker in here, and under that we have some device tree properties, which are these key value pairs in here, and then we have multiple other nodes under the root node. As you can see, there can be, each node can have more nodes underneath that and properties and so on. And this way, you can describe the entire tree topology of the system. But the thing is, it might just so happen that you need to reference another node from a node in the device tree, and that kind of turns the tree into a graph. Like you can see here, this is called the handle. So this, with that view, is referencing the 857 here. So it's not really a tree, it's a tree-like structure. But using this, you can describe the entire hardware to the software. Now, you use it in a few ways. One of them is it can load both Linux and the device tree, and then start Linux and just pass the device tree to the Linux or other software, other kernel. And this is not really interesting, but what you does there is just it can patch a couple of things into the device tree before it passes it to the kernel. Usually that's an Ethernet address. So you would have this ETH header, MAC address, variable, and if you are passing device tree to Linux, it can patch that variable into the device tree block. And that's our Linux, so we can share the same MAC address between you and Linux. But we are more interested in this device tree control thing. And what that is for is you can start U-boot and have it reference the device tree and read out the hardware topology out of the device tree super early on, and that way you don't have to encode any hardware specifics into the U-boot binary. Now, to understand at what point U-boot is able to read out the stuff from the device tree, we should go to the U-boot process. So what happens when you actually enter the U-boot binary and then move on to the init until you reach the U-boot shell. That's what this slide is about. So when you put power on this, you see it goes to the boot room or whatever first stage is until it reaches U-boot, at which point you land in the platform-specific init code. Now this is all assembly, and basically you land at the delivery vector where the U-boot is sitting. The platform-specific code resides in R/any whatever, and really it's responsible for doing the platform-specific setup. Now once that is done, it goes into the common C runtime setup code, which sets up the C runtime, and after this is done, it can jump into the C code. The first C code that's run is the support app, and it contains a list of functions which are running with the assumption that the system has very little So you will allocate at the end of the RAM once you finish the function, and starts or are the functions which are running with the assumption that you're already running in RAM and the memory constraints are not so bad. Now once you finish the board R, you will enter the shell, at which point the output will prompt starts and then you can interrupt it and enter the shell. The device tree is actually available ever since the first function in the board F list, so it's available way early in the usable process once you leave the assembly. This is operating in the actual flattened device tree, so unflattening does not happen. It can't happen because you don't have any memory for that. Nowadays you do, but on the old platforms you just didn't. There's a nice trick to at least in it list actually, in case you happen to have a problem in there, you kind of hangs in somewhere in there in the init space. You can hack up this init folder. See there are two debug statements in there. You just replace that with printf, and you can go print each init function it is calling, including its base address. And then you can find out which was the last function which was actually called. And run object dump to use binary, figure out what's the actual name of the function, and then look into the code and see what actually happened and why it's actually the wedge just that. So this is kind of neat, break out the init groups if you don't have a debugger attached to the system. Right, so now that we have the actually set up, if you look into the sources, you will see that there's like a gazillion of functions which are used to access the DB and it's still bleeding from the system, which sets, so this slide tries to make it more understandable. So you'll see that there are functions which use the FDD prefix. These are coming from the libfdd and they have like a boatload of boilerplate code all over it. You ideally shouldn't use them unless you need to do something really obscure with the device tree. Because you'll have to go around all boilerplate. So we kind of simplify that. That's why we have the FDD functions and they basically just pull out all the boilerplate from the FDD function, so you can just conveniently access the device tree nodes and pull out strings, values, and so on out of them easily. But you should only use that outside of the unit driver model. Now, if you're within the unit driver model, there are other functions which take the unit device pointer. They're the read function, and they allow you to pull out values from the device tree node associated with that particular driver, like its base address, its clock mapping, and so on. So outside of the device tree, outside of the driver model, you see within the driver model, you use that read function. All right, that's pretty much it. Now, the next thing is the user driver model. Okay, I don't have a good definition for what that is actually. So I'll tell you why it came to be. You see, back in the days of old, that means like 5 years, 6 years ago, the hardware started getting more complex, and the user was still at that point configured with macros. And all the drivers were basically just talking directly to the commands, so if you wanted to have 2 I2C buses with different drivers, you were just screwed. And people started like coding around that through some obscure hacks, and that didn't scale, so we were like growing this massive code base of hacks, so it just couldn't go on. So we designed the driver model at that point, and ever since then we're converting to that. To remove all the tags and allow people to use different drivers with multiple instances and so on. Now, the driver model is kind of similar to Linux, but not so much because we have some space constraints and so on. We want to keep it kind of small and simple. There are actually 3 objects within the driver model. One of them is uClass, unit class. Now, that one's responsible, well, that one is the API provider for the rest of the UBU. For a specific class of hardware. Think of it like a serial uClass is providing you, as a user consumer, stuff like put C, get C, test C, that sort of thing. It is also tracking all the driver instances, matching that specific uClass, which can provide these services. That means all the serial port drivers for the uClass serial. user can select which serial driver that U-Bus should call. Next things are drivers. Right, so these are the actual implementation of the register coding, which will get that service implemented. That means for a serial driver, it actually implements the FOSDEM for a specific kind of hardware. And finally, there are driver instances or devices. Now, these are instances of the drivers. You allocate some sort of structure with some data associated with that and register it with the class. So this also allows you to have two instances of a specific driver. That's not a problem. Register with the same class, just using different driving data. Now, the driver model core is actually designed to be rather lazy. So all it does during the initialization is it just registers the root driver. In case you have device tree control enabled, it just pulls the device tree and binds all the drivers into this tree hierarchy. That's pretty much it. It does not initialize any of the drivers. It doesn't initialize any of the hardware unless you explicitly call through a U class and access that hardware. Now this is to make sure that you do not initialize more than you really need to actually get to the next stage. Like, for example, you do not need to initialize PCI Express if you're booting from SPI flash, and the kernel is also stored in the SPI flash. So that's the intention here. Now, you have a convenient command menu which is called DM3, and that will show you all the drivers which are bound into the tree and also those which are probed. So in this case, in this system, you can see that the system has started. We probe serial console because we need to have that. I mean, this is printed on serial console, so we need the serial console to be made operational and probe. The serial port actually needs clock and pin control to be configured. That's right. The pin control drivers probe, and there's clock driver somewhere here as well in that list. And obviously everything up from there is also probed because that has to be available for these devices to work. Now, there are multiple states in which the driver can be. One of them is bound. That means it's available to you. You would actually see that device as available, and on the first call, the driver will actually get probed. That means the hardware will get initialized and all its dependencies will get initialized. In case you're implementing a new driver, you usually don't have to implement the bind and remove, bind and unbind functions because they will be replaced by the generic ones. Only in case you're doing something super specific, you might have to do something funny in the bind, but usually you don't need it. If you're implementing a new driver, you should implement probe obviously because you need to start out the hardware somehow, you need to focus on registers and so on. And often you also need to figure it out. So the remove function will be called when you execute, for example, to start it. Now, it can just so happen that you will have some funny hardware in case you do not deinitialize it before starting the kernel. It will do something obscure when the kernel tries to reinitialize the hardware. We had a situation where a USB controller did that. When Linux tried to reinitialize it, it was stuck in debug. The controller just vomited some rogue transmission into memory and just corrupted memory. It's really difficult to debug that, so you should implement the remove function. Right? Now, that should really explain all the basic concepts in you, I hope. And with that, we can go into the board sorting. So what I'll be doing here is do a really simple board sort. And you should do that. If you're doing board sorting, you should really start simple. Just get the serial port running in the beginning and do not add any fancy other stuff, because this will just introduce more variables into your board port, and you will not be able to make SSA also any failures. It will be just completely random. You can add all the functionality later when you have like a stable serial support, and when you can have poke around and you know that the board is stable. So that's not a problem. But at the beginning, let's just start with this simple stuff. So what do we have here? If you want to add a picture, you need to want R2 mapbar, which will be named your architecture. You should also support device tree in case your architecture is capable of that, and you should have support. We want at least one board devices will not be possible to use continuous integration to make sure that your code does not start page dropping. If you want to add one port, you need to add stuff into board / your manufacturer, vendor name / your board name, and then you will have to add a config file, make file, your board, the C file, which is like board specific stuff. Usually there shouldn't be that much stuff in the board specific file. Ideally that should all be in the device tree or in the driver. You will also have to add your board config into configs, so my test config, and you will also need to create a legacy configuration file because, well, some symbols are still not converted to things. Ideally there shouldn't be that much stuff in this file, and that would be increasing tests. You will need to add a link to your board config file into our our config tree to make sure that the config actually reads that board file. Alright. Something you might have to do in the process of reboot, there are actually board specific groups for the init process. They will read the files for those specific groups. Ideally, you don't need that, but if you do need that, well, that's what they are. And those groups should just go in the driver from the last week. Now, how to implement the uboot driver is actually not that difficult. All you need to do is define this sort of structure. We have this uboot driver macro here. You specify the name of the structure from this driver, and that actually gets put into a specific uboot linker list so that the uboot driver model can integrate over all drivers. And when you, for example, device tree probing, access all the compatible strings and so on. Then you have to specify name, the name of the driver, and the ID, which is the U class into which the driver fits. This is a serial port driver which I borrowed, so this is a U class serial. You need to specify ops. The ops have to match the name of the U class. So for serial U class, you will have some game serial ops. I'll show that to you in the next slide. Now, what do we have here? If you're matching the device to compatibles, you have to define OS match. Pro function, obviously, because you need to initialize the hardware. Primary data are actually allocated by driver model 4, so you don't have to call malloc in your driver. You just specify the size of your private data. In case you want to make sure that you can scope the driver from both device tree and board file using platform data, which may be convenient if you need to reduce size. Implement these two functions. This function which converts the device tree content to platform data, and then specify the size of the platform data which should be allocated. Again, the driver model 4 will do the allocation for you. So this is a serial port driver. There's a special flag which says the serial port driver should be available super early at the beginning of the process, because you may just need serial port output early on in case there's some bugs. Then in view with it, and then they want to spec some warning or something like that. Usually you need flag in your driver. Now, matching the device tree compatibles, that looks like this. You just provide the OF match table that's very similar to Linux. You can have metadata associated with that, so that when you mention some compatible, then the code can tell what compatible you actually matched onto. You can even toss pointers for this, so we can kind of have a structure associated with that. That's no problem. The function which is converting the device tree data to platform data looks like this. In this example, I just grab the platform data pointer, which is allocated by the DM4. I extract some information from the device tree, in this case that's the data address. If it's solid, then I just set it into the platform data base address. Now, once the code runs this function, the probe function can reference a flat database and just be sure that this is set with valid content. And finally, the implementation of the ops. Since this is a serial U class, we will be using the serial ops, which implement put C, get C. There's a pending character in the serial for FIFO and send software generator. The function is then implemented like so. The UX pointer coming in. You can get the private data, and there should be register probing here, but it's implemented in the serial data generator. So that's pretty much it for a serial port driver. Now, it may just so happen that you will want to have some even earlier debug serial console. You can enable that with debug UR, and it's really like this special stuff which doesn't even fit into the driver model properly, but it might come helpful. It uses its specific sets of print commands. It doesn't even use the print that's the standard print index and that sort of stuff. You have to implement this piece of code into your serial driver, which really initializes everything in the serial driver by hooking the registers directly. It doesn't bind on the device screen at all. And you have to implement the sort of C, which makes sure to emit the serial port, the character on the serial port. And so this is like super specific. It's probably convenient if you have like a debug UR dedicated one on that platform. Otherwise, you will most likely not need that. So just so it exists. The other thing is, if you implemented your serial port driver now with permanent squad, well, implementing the code driver is exactly the same thing. It's just B plus squad, and it has VM CLK options, which allow you to like enable disable clock, get and saturate, that sort of thing. So this is boring. I really won't get into it. I will show you how the consumer works. So the user of the clock framework uses CLK underscore functions, so CLK get right, saturate, and so on. Serial port driver, for example, can tap into it also. So let's see. Yeah, first of all, we need to get the clock handle. This is pulled from the log device tree property associated with the device. So you'll have in the device tree node for this serial port clocks property and clock names property. The clocks property will contain VM to the clock controller and possibly an ID of the clock. And the clock names property will contain this SDK string, so you'll be able to the clock framework will do that for you. It will look up which clock controller that is, and will fill up this structure accordingly. If that works out, then you will be able to use this structure to access those clocks and enable them. So what the enable will do is it will actually internally go to the new class CLK, find the matching clock controller, and call the driver model CLK name option with the specific clock ID in the clock driver. And that clock driver will then enable the clock. And if that works out, you can get to the clock with the driver. So another thing is the pin control framework. Again, implementing pin control drivers, the same thing as for the clock driver, serial drivers, just the same, easy. There's just a small quirk in the pin control framework in that, it implements two things. One of them is pin loop, the other is pin conf, and that can be kind of confusing. So pin loops is the thing which allows you to select which logical block in the CPU connects to a specific pin on the CPU, and pin conf allows you to select the properties of that specific pin, that means like voltage, pull up, pull down, that sort of properties. This framework implements both of them actually. You have to enable something like config DM things on family to have the extra functionality of it. It's again DM to control off. Consuming this API is a little different because in this case you do not poke specific pins in the driver, that would definitely work because different pin control controllers can do differently. Instead, in device tree you specify multiple pin control configurations, multiple ways to configure the pins with different properties and associated pin control names, and then in case the driver wants to set one or the other configuration of the pin, you just call pin control select state and select the matching state. So in this case, either UHS or default, so it's matching to this one. This specific case is an eMMC controller which is operating eMMC in either 3.3 volt setting or 1.8 volt UHS setting. iffy, and it's mostly old legacy stuff. So like Pyro or GMP framework is kind of iffy there, but the rest is pretty much okay. But enabling all that stuff may trigger some problems with size. So I would like to talk about low memory systems now. It could also be that even if you do not enable the device tree control driver model, you will run into some size limits. So that's kind of our problem. But anyway. Yeah, if you think of modern ARM SoC nowadays, it's usually what it does when it starts up is it loads a small piece of code into the OCRAM that's supposed to initialize the DRAM and load the next thing, right, into the DRAM and execute it there. So we support that with U-boot. It's called the U-boot SPL. It's really just a drop-down version of U-boot which fits into tens of kilobytes. You can have the SoC load tab. That's stuff which configures the DRAM, starts the DRAM, and then loads the next stage. Now the SPL is capable of loading either the full U-boot or it can load Linux directly to reduce your boot time. It's called the Falcon mode. You can take a look at that. The SPL doesn't have to have device tree control at all. It also doesn't have to have driver model. This is optional, but it can be enabled. Now you can configure both the U-boot and the U-boot SPL separately in your kconfig file using the config SPL prefix for SPL and config_prefix for full U-boot. In case this is still not enough, if the system has some limitations where the U-boot SPL will not fit either, you can use like a DPL, which is like terminally SPL program loader, and this is usually consistent with one-man flashes where the window from which the system is booting is like 4 kilos or 3 kilos, and this is like super specific origin. Starting it up, copying the rest of the content of the one-man flash into the CPU, so CRAM, which will then be the U-boot SPL, and then it will be the U-boot SPL. If you can avoid the DPL, that would be perfect because this is like super weak. And again, yeah, you can configure the DPL with something on this DPL. So you can have those free and configure them separately. That's not a problem. Now the other thing is, if you're using device tree in U-boot SPL, it can trigger again some size limits. So what we do at this point is we compact the device tree block. If you add these USB reload properties to the device tree nodes, you will not remove those nodes when you compact the device tree for the SPL. Otherwise, it will break out all the nodes which do not have this property to reduce the size of the block. If having the device tree support in SPL is still too much for you, you can remove it completely and just throw a platform data from your board file in the SPL. And the lookup technique is quite happy, so this will save you some size in the SPL. And yeah, that's pretty much it from me. I would like to kind of summarize it. So if you're doing U-boot port, use VM, use DP, use kconfig symbols. That's pretty much what I would like you to do if you're doing U-port. If the drivers are existing, don't write new ones. Just reuse whatever is available as new DD compatibles. For example, on some systems we use T-card controller drivers, which are written from completely different systems. Because that device is compatible, it's fine, it works, no problem. If you have some fixes, whatever, submit patches, it may just happen that it will not go in on the first try, but well, keep going. Run them through the driver CI before submitting, run them to check patch. And well, if you need some help, check the documentation, it's in the doc directory. If that's not enough, turn on my IFC, just ask questions, wait for a couple of hours because there may not be anyone in the IFC who's actually know the answer to the question, so wait a couple of hours. Usually someone will figure that out. And if the IFC is insufficient, submit message to the ML, submit package to the mailing list. That's pretty much it. So thank you for your attention and questions. Yeah, there could be some more specific tweaks to the system which are not present on all the other systems on that architecture. Like, we have some obscure LED which you need to turn on because it will indicate that your board is on. And you don't want to impose that on the other people. Yes. We're supposed to be FI and what is it? I'm using it all binary. I don't know about anything like that. No. We know that support using UBS FI library and talking about so Tuesday is actually using that to start drop and make it look kind of like any other drop system. Any other questions? Yes.
Why do you need to duplicate the Linux drivers and the device being used? Can you just use the Linux kernel drivers and VDS? Why you have separate? So sometimes something works with the code, doesn't work with the kernel, sometimes works with the kernel, doesn't work with the kernel.
Yeah, so yeah, that's a good question. So the question is, why do we rewrite our own drivers for you and don't just use drivers from Linux? You see, we're trying to do that, but it's impossible with all subsystems. So for example, the USB subsystem is now importing drivers from Linux and just adjusting them to match into the user driver model, which is slightly different. So yeah, we're still trying to do that. And regarding recycling device features from Linux, also we do that. We're just pulling in the device features from Linux.
There's always difference.
Yeah, there's always difference. There are some drivers which are just written from scratch, that's true.